So in the lesson that we're going to look at today, we're going to talk about how to solve or begin to solve definite integrals. And one of the ways that I have usually taught definite integrals in the past is talked about Riemann sums, and I'm going to not talk about that this year. We're going to try it out. Now, a lot of calculus teachers might arch an eyebrow at that. So if you're watching this lesson and you're not one of my kids, go investigate some Riemann sums. They are really interesting, and there's some good notation in there that you need to have. However, what I'm going to try and do is simplify this just a little bit so that we can see what's going on with the actual integral and not get lost in the summation part, okay? So this is integral formation that you see on this slide right here, and there are a lot of different ways to find it. But what we're going to do is we're going to talk about what integral notation is, how it works, and what it means. So with integral notation, it goes back to the Romans and this elongated S for sum. That's the sum part. And this is, if you squish this symbol down, you have an S shape for sum. The upper limit of integration is this top letter. The lower limit of integration is this bottom letter. And so basically what we're saying is we're going, all right, on a graph, we're going to sum up from A to B all the rectangles that we can squeeze in there. There you go. There's your Riemann sums. And when we do that, what we're going to locate is we're going to locate the area under the curve. We're going to discover what this area under this curve is by doing that process. We're going to sum up all those things to get that area. So some other things that we've got going on here. We start at A, we end at B. That's start at A, end at B. The integrand is the function inside, so you might have something that would be like, say if we looked at like 3x squared tan x. I'm not just totally making that up. We would look at that from an integral from, say, 0 to pi. So this is what an integral would look like. So my integrand is the function part, so this part here would be the integrand. The differential is this last part over here, the dx part, and x would indicate which variable we're actually working with. So if you're working with theta or with t or some other function, that guy is what would determine the variable that you're actually working with. So we could have something like the integral from 7 to 22 of 5x squared plus 7x minus 8 dx. Or if we didn't want to have all of those guys, we could maybe we're not working with x's. Maybe we're doing a problem where we're talking about angles or something like that. So we would have then we could have theta squared 7 theta d theta. Okay, and it's the exact same process. It's the area under the curve for this integrand right here. Well, maybe we aren't working with thetas. Maybe we're talking about some sort of time sort of thing where we're looking at like an airplane flying or a rocket launching or who knows, a boat over water. So maybe these are all t's. As long as all these guys kind of match right now for us, that's the important part. So what do we have here? We have the integral of f from A to B. That's what this whole thing is talking about, okay? And we're going to see a lot of these over the second semester now. So start getting comfortable with it. The big deal that we need to remember is this is area under a curve. And remember, there's lots and lots and lots of ways to find areas, especially if it's a geometric shape we understand, like a trapezoid or a rectangle or a triangle or a circle or half a circle. There's lots of different ways to find those areas. And we're going to investigate those ways first before we dive into the actual inner workings of the definite integral. These are inner workings, just a simpler form of those inner workings.